Well, hello there, Stat Nation. This is chapter 5, day 2, and this is the probability section of the AP Stats course. Probability is can be very confusing for kids, or for anybody really. And so I thought it best that I produce multiple videos on key sections of probability. You're going to want to stop this. You're going to want to go back, listen to it again. If you master it, it's very simple because the actual mathematics is just multiplying, generally speaking, or dividing or factorial. So it's pretty easy. So I'm going to show you Pascal's triangle. I'm going to have a calculator to do things, and I'm going to have the notes. Okay, so chapter 5, day 2. Here we go. Let me share my screen. Okay, so you'll see chapter 5, day 2. What I'm covering quite a bit of things. They're not tested that heavily, but I think they're super important background information for everybody to know. Okay, so it's nice. Again, you're going to want to stop the video and write the solutions out. And it's a lot easier for me to start with the answer key rather than writing it out myself because it's such a time killer. Okay. So let's talk about a few things. One is sample space, all right? So sample space is when you list all the actual outcomes. And I did sample space on all 6 of these. And of course, the sample size is the number of possible outcomes. In the most basic sense, probability is taking all the possibilities as the denominator, and the numerator is what you're looking for. So in a sense, it can be simple. So if you're asked a question like, what's the probability of getting 2 tails out of 2 flips of a coin? The answer is 1/4. You can see the 4 possibilities here, and one of the 4 is 2 tails. Somebody else might come along and say, well, you got to get a half the first time and a half the second time. That equals 1/4 as well. There's always multiple ways of doing probability. There's no one single way. There's usually 3 or 4 ways. And that's part of the fun is I often ask my students, try this, tell me how many ways you can solve this problem. And of course, they're all kind of related. All right. A fair coin 3 times is actually 8 possibilities. Now I want to show you something here. It's real subtle, okay, when we get done with these 3, okay? So those are the 8 possibilities: 3 heads, 2 heads, 1 head, and no heads. And then there are 4 flips of a coin, okay, which is, of course, is 4 heads, and then there's 3 heads, 2 heads, 1 heads, and no heads. No heads is, of course, all tails. What's interesting is I want you to see a pattern here, okay? So there is one way to get heads, okay? You see that? There's 2 ways to get tails, heads, and there's 1 way to get tails, tails. That 1, 2, 1 might start ringing a bell. For this one, there is 1 way to get 3 heads, okay? There are 3 ways to get 2 heads. Where do I have them? 1, 2, 3 ways to get 2 heads. And there are 3 ways to get 1 heads, which is right here and these 2. And there's 1 way to get no heads, which is called all tails. Look at that. And then here, there is 1 way to get 4 heads. There are 3 ways to get, there are 4 ways to get 3 heads. There's 6 ways, 1, 2, 3, I think 4, 5, I think that's 6. There are 6 ways to get 2 heads, 3 ways to get 1 head, and 1 way to get no heads with 4. Look at that pattern. Clearly, sample space is related to Pascal's triangle. So you might want to make a note to that. Pascal's triangle is embedded in this, which is kind of cool. So sample space is related to Pascal's triangle, okay? All right. So just wanted to slide that in there, something that you've known from your past. Okay. Now, the gender of 3 siblings gender of 3 siblings, okay? This is the exact same question as this one, okay? There's one way to get 3 boys, okay? There are 3 ways, I will circle them, to get 2 boys. 1, 2, where's the other one go? 3. There are 3 ways to get 1 boy. I'll circle them now. 1, 2, 3. And there is 1 way, which I will underline, to get no boys, which is called girls. 1, 3, 3, 1. That's row 3 of Pascal's triangle. Okay. Now, the next set is a little different. This isn't Pascal's triangle-ish. They want to know electing a VP, president and a VP from 4 choices, A, B, C, and D. Now, this one, the order does matter. So when the order matters, you are no longer doing something related to Pascal's triangle. This is a permutation. This is a permutation. Now, do you have to know that this is a permutation and that these were combinations? All of these were combinations. Do you have to know that to solve the problem? No, you don't have to know it, but it's kind of nice, okay? Permutations are related to factorials. Well, they're both related to factorials, but I'm going to really simplify this, okay? So electing a VP, A could go first, and you notice I have A with the 3 choices, then B with the choices, then C and D, and then I kind of kept going there. But if I listed them all out, there are what, 3, 4, 5, 6, there's 12 of these, okay? There's 12 of those. Now it should make sense to you. When you elect a president, there are 4 people that can be president. There's only 3 left that can be vice president. 4 times 3, 12. So it's pretty easy to come up with that, okay? But I think the sample space eliminates the need for thinking about, is this a permutation? Is it a combination? What's going on here? Just write out all the possibilities. Now, if all those possibilities are over, let's say 50, 100, it becomes very difficult. But when it's manageable sizes like these, it's okay to do problems just doing sample space, all right? Now, rolling 2 6-sided die, aha. We're setting up the game Craps, which is a really cool Vegas game. Notice that the 7 is the most common roll, and there are 6 7s, okay? And so I'm going to label these, right? This is a, this is a 2. This is getting a 2. This is getting a 3. This is getting a 4. When I say a 4 or a 5, I mean on 2 die when you add it up. 6, 7, here's an 8, 9, 10, 11, and 12. Okay, so there are 36 rolls, which should make sense. There's 6 on one die and 6 on the other. That's 36 rolls. Okay, so there's your sample space. That's a good example of sample space. And if you sense that a problem has a real small number of outcomes, sample space might be your choice to solve it. Okay, all right, so let me slide down here. Okay, with replacement and without replacement. With replacement, it's called independence. So when I say with replacement, you've seen these before in your math in prior years, I would assume, okay? With replacement is like you have a bunch of or you're rolling a dice. If you roll a dice twice, obviously you can hit the same number twice, it's replacement. If you're playing cards and you pull a king out, you're not going to get that same king again. That becomes a conditional problem, okay? All right, just some other vocabulary. That's simple. We'll get to this sort of later, all right? Now, fundamental counting principle, it's easy. It's just A times B, and I'm going to show you that, okay? And if we have A or B is when you are adding them together, okay? Pretty simple. And again, we're at the real basics here on probability. So let's walk through these. Let's walk through A, okay? We'll do A, B, C. So if we have an outfit, we have, you got to have 1 pants, 1 skirt, and one shirt and 1 jacket. You can't, wear multiple things there. So if in your closet you have 5 pants, 3 shirts, and 2 jackets, then clearly you have 30 different combinations, okay? This is how our students come looking different every single day to school, even though they wear the same thing, okay? 4 pants, 4 shirts, and 3 jackets, no problem, that's 48. You can see the math is real simple here, okay? Your class schedule, wow. If you got to have 1 of each. If there's 3 biology sections you could take, 4 math sections, and 5 English, you can see that's going to be 60. Again, pretty simple, okay? I kind of overkill this, but 4 sciences, 2 math, 3 English, no problem, that's 24. And again, stop the video, walk yourself through it. This is simple. C might be a little bit harder. If there's 10 true-false questions, true-false means there's 2 possibilities 10 times. So that would be 2 possibilities in the first question, 2 on the second, 2 on the third, 2 on the fourth. Ah, that's a pattern. There's 10 of those. That's 2 to the 10th, okay? And then 8 multiple choice questions, A through E. Okay, you can see the math on that. It's pretty common that, you know, especially in the old days when we did them on Scantrons, and I would see 2 kids that didn't know what they were doing at all, and they would have 8 consecutive questions that had the same answer. And they're, you know, got to make sure them right and wrong. And I'm thinking, what are the odds I have by chance? Not very good. So I would usually say something to them. Okay, so this one, if he had 8 true false ahead of time, that's 2 to the 8th. And then 6 multiple choice, that's 4 to the 6th. No problem. Fundamental counting principle. Just multiply the possibilities repeatedly to get how many total would be in your sample space. Okay, so I'm going to slide down. We're going to do these now. Okay, these are similar. Okay. License plates. You realize that, you know, I don't know all the rules of license plates. I don't know if they allow zeros and O's. I don't know all that stuff. So I'm just going with a real basic approach here. So for 7 characters in a license plate, if you're going to have 7 of them, there are 10 digits. 0 through 9 is actually 10 numbers. I think you're aware of that. So that's 10 to the 3rd. And then there's 26 letters, okay? And that'll be 26 to the 4th. That's a lot of license plates you can have. That's 456 million cars. That's a lot of cars per state, okay? So if it was only digits, only meaning numbers, that would be 10 to the 7th. If it's got to be a digit first, which then 3 letters, you can see the progression here, then 3 digits again. This is kind of the setup in California, is pretty much our setup, okay? So that's that. All right, phone numbers. Phone numbers, we'll go over to E. Phone numbers. So obviously the area code, everybody must be, if it must be 714, I mean, this is a little overkill. There's only one way to do 714. It's 714. And then if all the other digits don't matter, it's 10 to the 7th. That 1 to the 3rd might be confusing because has to be a 7, has to be a 1, has to be a 4. I mean, it's the same thing, it's just 1, okay? Digits 9 and 1 not allowed on a 10-digit number, okay? So there's 8 to the 10th because it's only 8 digits are left. And then the area code is 714 with no repeating digit. Okay, so there's only one way to write 714. Then you're going to go, nobody repeats. I've already used 3 letters, 7, 1, and 4. So there's only 7 left. Then there's 6 left. Then there's 5 left. Then there's 4 left. Then there's 3 left. Then there's 2 left. Then there's 1 left. Of course, that makes 7 factorial, something from your background. Okay, you've seen that before. Okay. All right, graduation order of 20 kids. Any order? Well, you can't be first in line and 50th and 20th, I should say, or first in line and 10th. So it's 20 factorial. All right, top 5 in any order. Okay, that's 5 factorial. Then the rest in any order times 15 factorial. As you notice, 20 factorial is not the same as 5 factorial times 15 factorial, just so you know. Well, valedictorian, only 1 kid. Salutatorian, only 1 kid. Then anybody in any order. There you go. Okay, again, feel free to stop the video. That's the purpose of this, to make it a little quicker. Okay. All right, now combinations and permutations. Okay. Again, doesn't pop up a whole lot, but can on the AP test. So we got to be ready for it. It's fairly unlikely that you're going to use these formulas. It's fairly unlikely, okay? Combinations, if you can write this down, they are related to Pascal's triangle, okay? And permutations, I like to use this phrase. I like to use the phrase partial factorials. Partial factorials. I think that's good. I like those two things, okay? So we've kind of seen Pascal's triangle. I got it ready for you. I got my calculator ready. We're going to show you some different things, okay? Combinations, order doesn't matter, okay? Like, order doesn't matter when you go to the playoffs. It doesn't matter if you finish first, second, or third. You're in the playoffs, okay? Where does order matter? Maybe in vice president, president, secretary, where the order would matter, okay? A horse race, order matters, first, second, and third, because the horses pay out differently based on first, second, or third, okay? But if you're saying, oh, the top 4 horses go on to the next round of races, then order doesn't matter because all you got to do is finish in one of the top 4. Combination, permutation. Now, to really make it simple, a pizza, you can get a combination pizza of cheese, pepperoni, onions, whatever. The order doesn't matter. Nobody walks into a pizza place and says, I would like to order a pizza permutation. Please put the cheese first, then the pepperoni, then the mushrooms. You don't do that. It's a combination. Order doesn't matter. Okay. Now, so I'm going to show you these a couple different ways, okay? I'm going to be flipping back and forth between something else. Okay, so 4A, creating a passcode for your cell phone. Your passcode is a permutation, okay? It is not a combination. You can't put the numbers, whatever your code for your phone, whether it's 4 digits for an iPhone, let's say you go 6813. You can't type it in a different order. Order matters. That's a permutation, okay? So when they say a passcode for your cell phone, they should say a pass permutation, not a pass combination, okay? Now, 4 female and 4 male students for city council, obviously that's a combination. It doesn't really matter when you're chosen or how you're chosen. You're chosen first, second, or last. You're on the school site council, and we have those groups, okay? And I gave you that wonderful pizza, which is a combination, not a permutation. Okay. Now, when kids are doing combinations and permutations, I don't think it's real likely that you're going to be doing it with factorials. I don't think. Now, on your notes, if I was you, I would write all these down, but I would also write the additional ways we're going to be doing this as well. There's some cool ways we're going to be doing this, okay? I'm going to show you with D and E and F, those are combinations, and those are related to Pascal's triangle. Okay, there's a couple of ways to do those that are practical. Okay, all right. So let's look at 5, choose 2. Often they say the word choose instead of combination. 5, choose 2. Okay, so let me go over to let's see here, Pascal's triangle. Okay, now let's label this real quick. I have this in my classroom. Sometimes kids will draw it out real quick because you can just do the adding real quick on it. Okay, so this is considered row 0, just so you know, row 0. This is row 1. Okay, so 5, choose 2. I need to go to row 5. Row 2, 3, 4, 5, right here. This is row 5. Okay, so you can start either way, but I always say start with 5, choose 5. 5, choose 5. Now, using your common sense, look at my fingers. If you have 5 fingers and you want to choose all 5, how many ways are there to do that? There's only one way. You choose all 5. There's the one. Okay. The next one is 5, choose 4. Same concepts, okay? If you have 5 fingers, look at my hand, you have 5 fingers and you want to choose 4 of them, then there's 5 ways to do that because you're going to leave one out each time, okay? All right, and then this is, of course, 5, choose 3, running out of, this is 5, choose 2, this is 5, choose 1, and this is 5, choose 0, okay? So as you can see, we're looking at 5, choose 2, which is 10 right here. So that's pretty easy. So I think you're most likely, like I said, to do combinations with Pascal's triangle. I don't think you're going to be doing this pattern. You might, okay? So that's 10. Now, if you want to get into your calculator, you can do that too, okay? All right, so you're going to go math, probability, and see. That's going to be what you're looking for, okay? Right there. All right, so let me clear this real quick. I'm going to go 5, math, arrow over to probability, go down to NCR, 5, choose 2. It's all ready for you. I'm going to hit enter. 10. That's another way to do that kind of problem, which is might be the way you do it. Okay, it's hard to say. I'm not sure what's easiest going to be for you. Okay, so with that, 8, choose 3. So if I have my Pascal's triangle handy, I'm going to go down to row 8. Now, row 8 is going to have 9 items, okay? And in this case, I think I'm going to be off the grid, okay? So 8, this was row 5. Notice that row 5 has 6 items, okay? And then row 6, row 7, row 8 is going to be down here. So I'm going to choose not to do that because I think that's kind of a pain to go through and do all that. So I'm going to then go to my calculator, okay? Which will be pretty easy to do. There we go. 8, math, probability, NCR, 8, choose 3, I think. 56. Got it. 8, choose 3 is 56. Okay. All right. And then for F, 11, choose 9. I'm not going to use Pascal's triangle. I know it's too far down the sheet. I'm just going to go ahead and use my calculator. You can do it this way and then do all of the canceling out, etc. It's no problem to do it that way. Okay. So 11, choose 9. I'm going to go to my calculator one more time. 11, math, probability, NCR, 11, choose 9, I think that's what it was. 55. All right, very cool. Okay, I'm going to take a second and explain combinations with free throw shooting, just to give you another example, okay? Just to give you one more concept of this, okay? So, and again, we know that combinations involves Pascal's triangle potentially. It also involves sample space. So let's try this if we want to. So let's say you're going to the free throw line 3 times, and I need you to make 2 to win, okay? How many different ways can you go to the free throw line 3 times and make 2? I'm just going to do simple sample space, okay? So a miss is an X, a make is an O. 3 free throws. I could miss. I could miss, miss, miss. I could miss, miss, make. I could miss, make, miss. I could make, miss, miss. Okay. Again, we're doing the boy-girl thing here, basically. Okay. That's 3 of them. Then I could make 2 of them. This is the one I'm after. I could make, miss. I could make, miss, make. And I could miss, make. And the last thing is make all 3 of them. Okay. So we got 8 of them there. Now, what I'm after is this one right here. Okay. So 3 choose 2 is 3. Now I know from Pascal's triangle that here is row 3. Notice row 3 has 4 items in it. And the reason is, in free throws, you can make none, you can make 1, you can make 2, you can make 3. So if you think about it, row 3 is going to have 4 items. Row 4 is going to have 5 items. And the reason is, if you use the free throw analogy, you could make none, make 1, make 2, make 3, okay? So here is 3 choose 3, 3 choose 2 right here. It's 3, okay? So there is an extra example for you for Pascal's triangle with combinations, okay? Now, permutations, I call them partial factorials because order matters. All right, 5P2. Let's say, here's the story on this. There are 5 teams in league. Okay, how many ways can the top 2 finish? All right, so 5 guys could finish first and 4 could finish second. The answer is 20. I look at this as, watch my pencil here, as 5P2 is the first 2 numbers of 5 factorial. The first 2 numbers of 5 factorial. So then this would be the first 3 numbers of 8 factorial. 8 times 7 times 6. That's actually a quicker way to do it. This one's a little rough. This is the first 9 of 11 factorial. This is the first 9 of 11 factorial. To me, that becomes a calculator problem. So I'm going to go ahead and go over to the calculator and do that, okay? So I'm going to go 11 math probability NPR for permutation, and then 9. So that will give you the first 9 of 11 factorial, okay? So there's the answer to that question. All right. Okay. Now, let's jump into some situations, okay? So I can get, yep, got them all in line there. Okay, so 4J. How many ways can we assemble a starting lineup given 3 centers, 4 forwards, and 7 guards? And this is old school basketball. We're going to play 1 center. We're going to play 2 forwards. And we're going to play 2 guards. The game isn't really played that way anymore, but this is an old problem, which I kind of like. Okay. So we got to choose 1 of the 3 centers. We got to choose 2 of the 4 guards, forwards, and we got to choose 2 of the 7 guards. So that's a combination problem. Okay. All right. Now, if you gamble, play Powerball, which you probably don't because you're under 18. Okay. How many ways can we select lottery numbers from 1 through 69 and 1 from 1 to 26? You probably don't know, but order does not matter in Powerball. If you get the 5 numbers, it doesn't matter how they are on the sheet. It's just you have them. So it's 69, choose 5. And then you got to hit that 1 bonus number, which is you got to pick 1 of the 26. So it's a combination problem again. Okay. All right, now again, this is another lottery question, 4L. How many ways can we select lottery numbers for Fantasy 5 from 1 to 39? That's just 39, choose 5. And again, it doesn't matter if you have all 5 on your slip of paper, you're the winner. It doesn't matter the order, okay? Now, this is crazy. How many lines can be created from 11 points? No 3 of which are on the same line from geometry. You can sit here and do this problem if you, sometimes I have the kids actually do the problem where they do all the lines and stuff, but it ends up being 11 choose 2 because 2 points make a line, okay? That's what it ends up being, okay? That's kind of a silly problem that's not really about data. It's just a Wayback Machine into your geometry days, okay? All right, for N and O, okay? There are 10 shows on your DVR that you haven't seen, but you only have time to watch 3. How many different choices of episodes can you watch? All right, so that question is a combination for sure. That's 10 combination 3, no problem. Now, These days, of course, we got a lot of things that are in order, okay? Sometimes you got to watch shows in order, which is why you binge watch. In the old days with sitcoms, it really didn't matter which order you watched them in because they're all just kind of independent, funny episodes. But now, that would be, if you got to watch them in order, that would be 10p3. Okay? All right. Oh, 80 songs in your music library. You guys have that. And only fit 12 in your MP3 player. Again, old school problem. You now have an unlimited amount of cloud space on your phone, but just go with it. How many different choices of songs can you create? Okay. 10, combination 12. Don't worry about writing the answer down. By the way, that's 6.0247 times 10 to the 13th. Don't even bother writing that. Just write this answer. That's fine. This is the same thing. 2.8858888858 times 10 to the 22nd. Okay. So how many different ways can you create? If they have to be arranged, okay, they have to be arranged. That's an order, 10p12. No problem. Okay. P, how many ways can we select 3 homeroom reps in a class of 35 kids? Okay. If you have 35 kids and you want a little homeroom rep, that's just, doesn't matter what order they're in. That's just 35C3. I would go to my calculator. That would be brutal on Pascal's triangle to get down to row 35, okay? 4Q, a box of 20 calculators to contain 6 defective calculators. How many ways can you buy 5 calculators and get all good? Okay, all good calculators is basically this one right here is of the 14, you chose 5 good ones. And of the 6 that were bad, you chose none of them. And by the way, 6 choose 0 is 1. This, by the way, is 1. So you don't even need to really have it, okay? And you can see all good units, all bad units. Okay, so maybe erase this. The all bad unit one would be, all right, of the 6 bad ones, you chose 5 of them. And of the 14 good ones, you chose none. Okay? And then C, 3 good and 2 bad. This, again, that's right here, 3 good and 2 bad. Of the 14 good ones, you chose three of them. Of the 6 bad ones, you chose 2 of those. Okay? And at least 3 good ones. At least 3 means, I'm over here now. At least 3 means 3 good ones, or 4 good ones, or 5 good ones, or 6 good ones. Okay, 3, 4, 5, 3 or more. Okay. Let's see. Oh no, you're only buying 5. My bad. Only buying 5 calculators. 3 or 4 or 5. Okay, so I'm going to erase this and slide down and watch this. Okay, so this is how you buy 3 good ones and 2 bad ones. This is 4 good ones and 1 bad one. And this is 5 good ones and no bad ones. Okay. And or means plus. Lots of ways to do that. All right. Okay. Moving along. Lots of example problems here. Probably too many. Okay. There are 8 honor students to select from. If you select 5 of them, how many times larger is the possible permutation and combination? Okay. Okay. There are 8 honor students to choose from. If you select 5 of them, how many times larger is the possible permutation? All right. So we want 8p5 to begin with. Okay. And we're going to divide that by 8c5. And it's quite a bit larger, by the way. Permutations are larger than combinations. Okay? Okay, same idea on S. You will select 10 books to read from a card of 18. How many times larger is the possible permutations and the possible combinations? There we go again. Okay, and this symbol right here is divided by. Okay? That's probably just a calculator problem. Just punch it in. Okay. Hopefully that helps you. That is Chapter 5, day 2 of probability. See you later.